In this videocast, we'll look at what happens when we add an acid or a base to a buffer solution. Please make sure you have your sample calculations or sample problems paper in front of you while we work these problems and write down the notes. The first question says, a buffer is made by adding 0.3 moles of acetic acid to 0.3 moles of sodium acetate to enough water to make 1 liter of a solution. The pH of the buffer is 4.74. Calculate the pH of the solution after we add NaOH to it, after we add HBr to it, and for comparison, calculate the pH that would result if 0.02 moles of just HBr were added to 1 liter of pure water. Let's work this problem backwards and let's take a look and find out what is the pH. What is the pH if we have 0.02 moles of HBr in 1 liter of pure water? Let's take a look at letter C first. Make sure you have a calculator out. You can follow along as well. In letter C it says, okay, we have HBr, and we're going to add it to some pure water. Whoops, H2O. Remember, HBr is a strong acid, so it's going to completely dissociate in water and give us H3O plus and some Br minus. H3O plus and Br minus. And if you'd ice table this one, remember it's a strong acid. It tells us if we have 0.02 molar in 1 liter, we'd have 0.02 molar concentration of this stuff to start with. And since it's a strong acid, we lose all of this, and we would gain all of it over here. We would gain all of it over here. And so you'd end up with none here, and 0.02 here, and 0.02 here. And the thing, of course, that the pH depends on is the H3O plus ion concentration. And so if this is 0.02 molar and there's none of this left, to find the pH of it, we'd simply take the negative log of the H3O plus ion concentration, which would be the negative log of 2 times 10 to the negative second. If I move this decimal place over 2 places, it's 2 times 10 to the negative 2. So if you want to do this really accurately on your calculator, you can type in negative log 2 enter exponent negative 2, and you end up with 1.7. So the pH of this solution is below 2, 1.7. Now let's find out, this is if we just add HBr to pure water. Now let's find out what happens if we add this same amount of acid to a buffer solution of acetic acid and sodium acetate. Now a buffer, of course, is something that resists change in pH, and so we should see that it should resist it enough to be higher than 1.7 anyway, because remember the buffer solution starts at about 4.74. So let's work letter B now. In letter B it says, what's the pH of the solution after 0.02 moles of HBr is added? Now, when you add an acid or a base to a buffer solution, the first trick is figuring out what equation do I write. And the equation that you want to write is to take whatever is added, in this case an acid, and add the opposite thing to it. Because remember, a buffer solution is made of a weak acid and its conjugate base, or of a weak base and its conjugate acid. In this case, our weak acid is acetic acid, and our weak base is the acetate ion that's going to form when sodium acetate is dissolved in water. So HBr, being an acid, is going to react with the basic portion of the buffer. And the basic portion of the buffer is the C2H3O2 minus ion that's in solution. When this reacts, it's going to have a gigantic equilibrium constant because it's all going to shove to the right, because the H is going to very willingly be donated to this base, and we'll end up with some HC2H3O2 and some Br minus on this side. Now we can ice table this, and we can say, okay, initially I start with 0.02 molar of this. And if I look back up at the top of the problem, I'm told that there are 0.3 moles of the base. 0.3 moles of the base. And I'm also told that since it's a buffer solution, there's some of this acetic acid in it, because remember, the buffer solution is a combination between the weak acid and its conjugate base. So there's 0.3 molar of this stuff, and there's none of this Br minus to start with because it hasn't dissociated yet. Now when the buffer buffs or reacts to absorb the acid, we're going to use up the acid, so 0.02 will go away. We'll lose 0.02 on this side since it's a 1-to-1 ratio, and we will gain 0.02 on this side, and we will gain 0.02 on this side. We'll end up with none here. 0.3 minus 0.02 is 0.28. Here 0.3 plus 0.02 is 0.32, and we'll end up with 0.02 of the Br minus. And right now is probably a good time to address this situation. What do you do with the Br minus? Does that affect the pH? Well, ask yourself the question, where did Br minus come from? Br minus came from the strong acid, HBr, so it will have no significant want to grab a hydrogen from anywhere. It will act as a really, 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 really poor conjugate base, and so it's not going to do anything in the solution. It's simply going to spectate. Remember, if it's the anion of a strong acid, or if it's the cation of a strong base, it's not going to be effective or do anything in the solution. So anyway, if you're a good recognizer now, you can see that what we have left over at the end is an amount of a conjugate base, or an amount of a base, and an amount of a conjugate acid or an acid. The acid is acetic acid, and the base is its anion, or some people call it the conjugate base, or some people call this the base and its conjugate acid. If you have a conjugate acid-base pair, there's a really cool equation you can use to find the pH directly. The equation is called the Henry-Hasselbeck equation, and it works for all buffer solutions. And the equation says that pH is equal to pKa plus the log of base over acid. And so if we plug in these numbers, to find the pKa of it, we need to know the Ka, and we'll take the negative log of it, and the Ka of acetic acid is 1.8 times 10 to the negative fifth, and then we'll add to that the log of the base over the acid, and the base in this case is 0.28 molar, and the acid is 0.32. Now you can take out your calculator and you can punch in the negative log of this. You can divide this and take the log of it, add the two together, and you should know the pH. And if you run this through your calculator, you get the negative log of 1.8 times 10 to the negative fifth to be 4.75. And to that you add the log of these two divided numbers, which turns out to be negative 0.05799. And if you add these two together, you end up with a pH of approximately 4.69. Notice this pH compared to the pH that the buffer started at, 4.74, is not a whole lot different. It's not a whole lot different. Which makes sense because this is a buffer solution. And if you remember back to the problem we did a little while ago, if you just add this same amount of acid to water, you ended up with a pH of 1.7. Wow, buffer works pretty good. That's exactly what a buffer is supposed to do. Let's work letter A now, and we'll see if we can set this one up as well, because in this problem we're told that we're adding 0.2 moles of NaOH to the solution. And the trickiest part of these problems is the first step, initially figuring out what is the equation that I should write for the equilibria. In this case, a strong base is added to a buffer system that contains a weak acid and its conjugate base. Well, which thing is the strong base going to react with? Is it going to react with the weak acid, or is it going to react with this weak base? Hopefully you're knowledgeable enough to know that a base likes to react with the acid, and so you can write the equation of NaOH is going to react with the weak acid HC2H3O2, which is inside of the buffer, and you'll get a neutralization reaction where Na comes together with the C2H3O2, and the H and the OH come together to form water over here on the right hand side. So you can write an ice table for this. I guess I should say one more thing about this, because there's many problems that you do where you add an acid or a base to a buffered solution. And the trick is just to look and see if it's a base, you're going to add it to the acid part of the buffer. If it's an acid, you're going to add it to the base part of the buffer. And you have to be okay with figuring out what part of the buffer is acidic and what part is basic. Okay, so if you ice table this, you're starting out with 0.02 moles of this. You know that you have 0.3 molar of this concentration in the buffer solution to start with. And if you look over here, you've got to understand that the Na and the C2H3O2 minus are going to separate, and Na is just going to be a spectator. And so you know that this is already contained in the solution as part of this weak base. So you have 0.3 molar of that to start with, and water we're not really going to care about because it's just a pure liquid, and remember, those never go into an equilibrium constant expression. So when the buffer buffs, it's going to use up the 0.02, so you'll lose 0.02 on this side, and you'll gain 0.02 on this side, and you end up with none of the NaOH left, and you end up with 0.28 of the acetic acid here, and you end up with 0.32 of the acetate ion over here. Now, if you're a good recognizer, and you should become a good recognizer after doing a number of these problems, you can see that we have some weak acid remaining, and we have some conjugate base remaining. Weak acid and its conjugate base pairs are called a buffer solution. You can directly calculate the pH of this by using the Henry-Hasselbeck equation, which is equal to pKa plus the log of the base over the acid. And if you plug these numbers in from last problem, we know that the pKa of acetic acid is equal to 4.75. And then we take the log of the base, and the base concentration in this case is 0.32. divided by the acid, which is 0.28. And you can tuck that into your calculator. And when you put that in your calculator, you get 0.05799. Add that to the 4.75, and you end up with a pH of 4.808. Notice how the pH, once again, is not significantly changed from the beginning. If you look at the problem, the pH of the original buffer was 4.74, and even after adding 0.02 moles of a strong base, it ends up at 4.8. Not a huge change. Nothing like when we did the pH here of just adding a strong acid to water. Let's now take a look at one of your problems that you'll be assigned to do during class, number 26 in chapter 17. It says a buffer solution contains 0.12 moles of propionic acid and 0.1 mole of sodium propanoate, and it gives the formula for each, and it tells you that it is in 1.5 liters of water. Question A says, what is the pH of this buffer? And then we'll set up letter B, but I don't know if we'll get it completely done. It says, what is the pH of the buffer after the addition of 0.1 moles of NaOH? Something similar to what we just did. So we're told that we have propionic acid, 0.12 moles of that, and we're also told that we have 0.1 moles of sodium propanoate, and it happens to be in 1.5 liters. First step to doing these problems I always recommend is writing down the number of moles or the amounts of the stuff that you have dissolved in water. Once you've done that, recognize that this is a weak acid, and this will dissociate in water because it's a soluble salt. Remember, sodium, potassium, rubidium, cesium, and lithium salts are always soluble. And when this breaks up, it's going to give me some Na+, which will do nothing in solution because it came from a strong base, and it will give me some C3H5O2-, which is the conjugate base of this weak acid right here. Hey, we have a conjugate base weak acid pair. You can calculate directly the pH of this because it's known as a buffer system. Become a good recognizer of buffer systems, and it becomes real easy to apply the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the base part of the system divided by the acid part of the system. So you have to look up the Ka of propionic acid in the back of the book because they don't give it to you, and take the negative log of the Ka, and then to it you'll add the log of the base concentration divided by the acid concentration. But watch this. This is kind of interesting. It told you in the problem that there's this many moles of each, both dissolved in 1.5 liters. So if I wanted to find the concentration, I'd take my moles of my basic solution, which is 0.1 moles, divide it by my liters, which is 1.5 liters. That's my concentration of my base, and divide it by my acid solution. Notice I'm told that I have 0.12 moles of acid, so 0.12 moles of acid divided by my liters of solution, which is 1.5 liters. What's going to happen to both of the 1.5 liters? Well, they cancel out. So it's kind of interesting to note that you could do the Henry-Hasselbeck equation without converting to molarity, because the volumes, as long as they're dissolved in the same bucket, which they need to be, are just going to cancel each other out. So if we look up the Ka in the back of the book for propionic acid, is 1.5 times 10 to the negative fifth. Take the negative log of that, and you end up with 4.8. This gives you the pKa. Once you have the pKa, you can put that into the Henry-Hasselbeck equation, and pH is equal to the pKa plus the log of base concentration over acid, and it's 0.1 divided by 0.12 because this is our base concentration, this is our acid concentration. Plug this into your calculator, and it's 4.8 plus the log of 0.83333 repeating. Take the log of that and add it to 4.8. Add those two guys together, and you end up with about 4.7 for the pH of the base. The rest of the problem is really similar to the other problems that we did as sample problems, where you add either an acid or a base to the propionic acid. And if you take a look at the letter B in the problem, they tell you what is the pH of the buffer after the addition. What is the pH of the buffer after the addition of 0.1 mole NaOH. So now you're going to add a strong base to it, 0.1 moles of that. And so if you're taking a look at your buffer situation, you're going to add some NaOH to it. And when you add NaOH to it, what part of the buffer is going to react with it? Well, you have two choices. Either it's going to be the HC2 or HC3H5O2, the propionic acid, or the C3H5O2 minus propionate acid, the ion of the acid. Anyway, this is the acid and this is the conjugate base, and which thing do you think would react with the strong base? Well, of course it would be the weak acid. So you have to write your equation of the strong base with the acid part of the buffer solution. You'll get one huge arrow going to the right. And then, of course, the buffer will buff, and the acid will react with the NaOH of the OH portion of the NaOH, and you'll get some water. And then you'll also get the sodium propanoate, C3H5O2 minus, I'll write it as. And then, of course, you'll have some sodium ion that will spectate and do nothing in solution. Write a nice table for this and put in your amounts that you have, starting for the buffer of this, and the amount of NaOH that you're adding, which I believe is 0.01 moles. I can't remember for sure. And then you do your subtracting. When you're done, you should end up with some of this acid and some of this base right here. Those two things right there, of course, form a buffer solution, and you can find your pH using the Henry-Hasselbeck equation. So to summarize, when you do buffer type equations, step number one is the hardest, and that's always to figure out what kind of equation you're going to write. Remember, if it's just the pH of a buffer solution, or two things stuck together that form a buffer, you can skip that step. But if it's something being added, an H-containing thing or an OH-containing thing, a strong base or a strong acid, remember the opposite portion of the buffer is going to react with it. Step number two is to do an ice table once you've added the H acid-containing thing or the OH base-containing thing to a buffer, and find out what's left at the end. At the end, you should have part of the acid part of the buffer, part of the base part of the buffer. If you don't, then what's happened is the buffer's been broken. The buffer's been broken, and you'll have only the acid or the base that you've added to the solution left, and then your problem is just to figure out what the pH is of the strong acid or the strong base, which you've done before. And then step number 3 is to find the pH, and there you can use the Henry-Hasselbalch equation as long as you have some of the strong acid, some of the weak acid and the conjugate base remaining, or vice versa, depending on what the buffer is. So keep those 3 steps in your mind when you're doing buffer calculations.